Hello students, in our last video we saw that magnets have magnetic field. So how does this magnetic field look like? Let us perform a simple experiment using a bar magnet and a compass to visualize how a magnetic field looks. Fix a sheet of white paper on a drawing board. Place a bar magnet in the center. Sprinkle iron fillings uniformly around it. Observe the pattern made by iron fillings. We observe that iron fillings have arranged themselves in curved lines that originate at one pole of the magnet and end up at the other pole of the magnet. The greater force of the magnet, the greater the amount of iron fillings clinging to the magnet. If we draw a diagram of these iron fillings, it looks something like this. These lines along which the iron fillings align themselves represent magnetic field lines. Thus, a magnetic field line is a curve drawn in the magnetic field which gives the direction of the magnetic field. The lines start at the north pole and end at the south pole of the magnet. The space around the magnet in which the lines are spread is called the magnetic field. By drawing magnetic field lines, we can also see where the magnetic force is the strongest by observing the concentration of magnetic field lines. The area where the line concentration is more, the magnetic field is strong accordingly. As you can observe, the concentration of lines is maximum at the poles of the magnet, which shows that the magnetic field is strongest at the poles. Is there any other way of obtaining magnetic field lines around a bar magnet? Yes, you can draw the magnetic field lines with the help of a compass also. A tedious way of tracing magnetic field lines is by tracing the pattern formed by iron fillings around the bar magnet. An accurate method of drawing magnetic field lines is by using a compass. What will happen if you place a compass near a bar magnet? When we place a compass near a bar magnet, the compass needle gets deflected. The angle of deflection depends on which part of the bar magnet is near the compass. The magnetic field direction is the direction in which the north pole of the compass needle points or deflects. While moving the compass from north pole of the bar magnet to the south pole, mark the deflections of the compass needle. Plot similar points from the north end to the south end of the bar magnet on the other side. Join all the points marked on the paper. What do they form? Yes, smooth curve. Repeat the above procedure and draw as many lines as you can. You will get a pattern. These lines represent the magnetic field around the magnet. These lines are known as magnetic field lines. Did you notice the intensity in deflection in the compass needle? The deflection increases as the needle is moved towards the pole. What can you conclude from this observation? We can conclude that the strongest magnetic force is experienced at the poles of the magnet. So the next question is, what are the properties of these lines? Let us look at them. The direction of magnetic field lines outside the magnet is from its north pole to its south pole. And inside the magnet, the direction of field lines is from its south pole to its north pole. So magnetic field lines are closed curved lines. The density of field lines indicate the relative strength of the magnetic field. The more crowded the field lines are, the stronger the magnetic force. Another interesting thing to know will be whether two field lines ever intersect each other. The answer is no. Two field lines will never cross each other. When mapping the magnetic field, you will come across points where the compass needle does not point to any particular direction. This indicates that there is no net magnetic field at that point. Such a point is called the neutral point or the null point. So students, we have learned that magnetic field lines are closed curves around a magnet. We also learned about the properties of magnetic field lines. Remember that magnetic field is a quantity that has both a magnitude and a direction. In the next video, we will see the magnetic field of a current carrying state conductor.